Welcome to Chapter 9 of Converging and Diverging. This problem we're going to be solving using the alternating series test. So basically what that means is take the limit as n approaches infinity of the absolute value of the function. Basically what this does is it takes this alternating sign, -1, and it basically determines that to be just 1. So it's 1 over 7 plus 2n, limit as n approaches infinity. And basically, in order to use this alternating series test, you gotta write a little statement that says terms alternate in sign and decrease in magnitude to 0. That's basically saying that as this n increases, basically it's going to keep alternating in sign, and it's going to get smaller and smaller and smaller, approaching 0. So basically, this limit statement, when you plug in infinity for n, it's just going to equal 0, which will make it converge. Converge by the alternating series test. Now, this problem isn't done just yet, because does it converge conditionally or absolutely? And the only way to do that is to take the absolute value of this equation and just set it up and solve right here. Now basically, this will diverge, or we're going to set this up by comparing it to 1 over n using the limit comparison test. And basically, this 1 over n is going to diverge by the p-series because it's 1 over n to the p, and since p is equal to 1, it diverges. Alright, so now what you do is you take the
Wait,
limit.
stop. You missed a step.
No, I didn't.
Yes. Yeah, you did. Is this by limit comparison?
Yes. I'm writing that out, Kevin.
You have to compare them.
I'm comparing. Kevin.
At limit comparison, you have to compare them.
Kevin, oh my gosh. No, I'm telling you, you put this one over this one.
Yeah.
Kevin, that's after this step.
No, you compare them first to see if it's positive and finite, and then you find then you see if the one you compared it to diverges or converges.
Doesn't matter. So that's just gonna equal
Amateur.
1/2. Psych, it's gonna equal 2. And since this is positive and finite, then this is going to also diverge. So basically what we learned, since it converges by the alternating series test, but diverges by the limit comparison test, it converges conditionally. Thank you. We have this series, basically cosine of 2 pi times n over n cubed. So basically cosine of 2 pi equals 1. So then you're just going to have n over n cubed, and so that's going to cancel into 1 over n squared, which is going to converge by the p-series because p is greater than 1. Okay, so here we have this geometric equation, 3 times 1/3 to the n, and so basically this is just going to be r, and so r equals 1/3. Since r is less than 1, it converges by the geometric series test. So for here we have this equation, 1,421 over 300 to the n plus 1. So what we're going to want to do is we're going to split it up. So it's 1,421 over 300 times 1,421 over 300 to the n. which in turn is a geometric series. So that's going to make r equal to 1,421 over 300, which is greater than 1. So it in turn diverges by the geometric series because r is greater than 1. Thank you. For this series, n to the 1 minus 3n over 4 to the 2n is going to be very difficult. We're going to be using the ratio test. And basically what we're going to do is we're going to take, the obvious a to the n plus 1 over a to the n. And basically, so that's going to leave us with this equation. And now we can do some canceling. 4 to the 2n can cancel with 4 to the 2n, leaving us with 4 squared, which will turn into 16. So then we have n plus 1 to the negative 2 minus 3n over 16 times n to the 1 minus 3n, which this will reduce to this. And basically we can cancel this n to the negative 3n and n minus plus 1 to the negative 3n because they will go to the same place. And then basically if we bring this n plus 1 down, it'll be 1 over 16n times n plus 1 squared. And the limit of that will equal 0, which is less than 1, therefore it will converge by the ratio test.
Alright, so this problem, negative 1 to the n times 4n over 14 n to the third plus 3n squared. We can tell that this is probably going to be an alternating series problem because again we got the negative 1 to the n. That's kind of the tell-all sign of alternating series. So we're just going to try that. So we'll put everything, the limit of n is going to infinity, and then we'll put in an absolute value, essentially just taking this out. So we got to put this in here because we won't be thorough. And so yeah, now through this process, the negative 1 to the n is taken out, and we have 4n over 14n cubed plus 3m squared as the limit of n goes to infinity. So basically we can cancel out an n here. So this becomes n squared and this becomes n. And then it's 4 over n, which is always going to be 0 when n is going to infinity. So this again alternates in sign and decreases in magnitude. Magnitude's the word you gotta remember there. To 0. So therefore converges by the alternating series test, but we're just gonna say AST because we gotta get moving. So the thing about these problems is we're not done yet. We also have to figure out if it converges conditionally or absolutely. So by doing that, we're going to have to figure out whether it converges absolutely or conditionally, because we already found out it converges, but again, it's an alternating series. So we have to figure out what type of convergence. So now we just take out the negative 1 to the n and just try to solve it like this. So 4n over 14n third plus 3n squared. So the first thing I'm going to do is I'm just going to take out the n and n in the function. So then we get 4 over 14n squared plus 3n. And now I'm just going to use the limit comparison because I think that will be the easiest way to solve it. So we just go to infinity again, and then we have 4 over 14n squared plus 3n, and then we're going to cancel that by just using a very simple function, just n squared over 1. So since the first terms in both of these are n squared, these will cancel each other out, and then we should get, this becomes 1, and this becomes 14, because the 14 is what n is multiplied by. So then we get 4 over 14, which is going to be 2/7. And then again, that's finite and positive, so that means that the limit comparison does work, and we can use that new formula, 1 over n squared. So now we're just going to create a new formula here, and that becomes 1 over n squared. And then what is this? This is a p-series. So now we're just going to say the p is equal to 2, which again is greater than 1. Therefore, it converges by the p-series test. Which then means that therefore this function is going to, sorry, I got sidetracked there. It's going to converge by the limit comparison test. So let me just write that up there, and then it should be done. Converges by limit. All right, so, oh wait, converges absolutely, I completely forgot about that. So since it converges both ways, that means it converges absolutely. So yeah, there you go.
So basically for this problem here, we have 1 over 3 plus 1 over n to the nth power, and since it's to the nth power, we'll be using the root test. So basically here, take the limit as n approaches infinity of the nth root of the series. So basically, these roots will cancel with each other, so you're left with 1/3 plus 1 over n, which basically as n approaches infinity, turn this into a big fat 0, and then it'll just be 1/3. And since 1/3 is less than 1, this series will converge by the root test. Okay, so we're finding the divergence and convergence of this series, n cubed plus 5 over n to the 5th plus 15, so we're going to do the limit comparison test. We'll be comparing it to 1 over n squared, which converges by the p-series, because since p equals 2 and 2 is less than 1, it converges. So basically, we're just going to do the limit, sorry, that's a limit, as n approaches infinity of the function times divided by this function. So basically that's going to equal 1, which is positive and finite. And since this converges by the p-series, this will also converge by the limit comparison test. Okay, so for this we have 1 over n to the 7th plus 2n cubed plus 1, and we're going to be using the direct comparison test. We'll be comparing it to 1 over n to the 7th. 1 over n to the 7th is greater than n to the 7th plus 2n cubed plus 1 because they're adding this stuff, which is in the denominator, which is making the fraction smaller. So basically, 1 over n to the 7th will converge by the p-series because 7 is greater than 1. And so basically that's just saying that this okay, so basically we have the summation of 1 over 4n squared minus 1. So basically that's going to be a difference of squares. So you're going to have to set it up to be 2n minus 1 times 2n plus 1 on the denominator, which you know can be used as partial fractions. So basically you're going to split up into a over 2n minus 1 and b over 2n plus 1. And so basically what you're going to do is you're going to multiply these cross, so multiply that by each other and these by each other. So you get a times 2n plus 1 and b times 2n minus 1. So basically you're going to put in negative 1/2 for n, so this is going to be 0. And this is going to be negative 2. Negative 2 equals 1. And then b will equal negative 1/2. Do the same thing for 1/2, that'll equal 0. Then a will equal 2. Or 2a will equal 1. A will equal 1/2. So then basically we have this right here, which is just a, which is 1/2, over 2n minus 1, and then b over 2n plus 1. And so this is going to be a telescoping series. So basically you're going to take the limit as n approaches infinity of all these terms, and so you're just going to write out 1, negative 1/2, negative 1/2, 1/2, 1/6, negative 1/6, 1/14, and it'll continue all the way until you get to these. And then basically what you're going to do is, since they cancel out because you're plugging in numbers for n, you are going to take the limit as n approaches infinity, negative 1/2 minus 1 over 2 times the quantity 2n plus 1, which will equal negative 1/2 meaning this converges by the telescoping series to 1/2.
Alright, so here we have n to the third over ln of 3 to the nth. So for this one, we're just going to use simple ratio tests to solve these. So we're going to set n going to infinity as the limit, and then we're going to put in an absolute value, and then we're just going to put these terms, if they're n, they go to the n plus 1. So this becomes n plus 1 to the third, ln of 3 to the n plus 1, and then we multiply it by the original function but flip. So then we get ln of 3 times n over n third. And so then you can cancel out these because they're both to the third. And then this one, you cancel out the n, and then you just left with it to the 1, which is just the function right there, ln of 3. And then you get 1 over ln of 3, which approximates to 0.91, which as you can see is less than 1. So that means since it's less than 1, therefore it converges by the ratio test.
So basically we have this series right here, n squared over n to the 4th, and basically that's going to simplify into 1 over n squared, and this is going to converge by the p series because 2 is greater than 1.
Oh, whoa, I didn't see you there. Hi, I'm Niall. And today we're going to do another calculus problem. So this one, just by looking at it right now, it looks like we're going to use the integral test because clearly this looks like what you would see in a u substitution if these were x's and this was like an integral. So we're just going to do just that. We're going to set it up in an integral form now, but we're going to make sure that we have the limit as n is going to infinity, because you see that up there, that's the infinity symbol right there, which means that it's going to infinite terms. And so then we're just going to use the substitution method where we put a 1 here, and then b, and b is going to represent the, or shoot, we're going to change this to b, I'm sorry. So this is going to be b, and b is going to infinity. And then we're just going to put 2n over n squared plus 1. And now, since we've got it in an integral form, it's pretty simple. We're just going to use u substitution. So the u is going to equal our n squared plus 1. And then the derivative of that, the du, is going to be 2n d. Sorry, there should also be a dn right here. And then, so yeah, once we put in u substitution, it becomes du, or dn, sorry, dn, or no, wait, it's still du over u, and you know what that means? That means that we're going to use an integral, or sorry, not an integral, we're already using an integral, we're going to use a logarithm. So that becomes, once you integrate this, this becomes ln of n squared plus 1. And then we still got our boundaries b and 1. And then we got to make sure to remind ourselves that b is going to infinity. So now we're just going to plug these terms in. We subtract top from bottom. So we have ln of b squared minus 1, or plus 1, sorry, minus the ln of 1 squared plus 1, which will just be ln of 2. And so, obviously, if we're doing the ln of infinity, that's just going to equal infinity, because we've got b is going to infinity. And infinity minus anything is still going to be infinity, which means that the solution to this integral is infinity. And by the integral test, if it's not a rational number, if it's infinity, that means that it diverges by the integral test. So therefore, 2n over n squared plus 1 diverges by the integral test. Alright. you for listening.